Well, 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 what do we have here? Boom! We got a couple triangles on a graph. Patriotic because they're red and blue. Well, our problem for today is shown here, and this is in your notes book too, on I believe page 186. It says in the diagram below, triangle PQR, the red one, is similar. There's the word similar here to triangle LMN. Describe the sequence of transformations that transforms triangle PQR to triangle LMN. So in this lesson or this day, we'd like to well, kind of recap dilations. That was in our last day, last lesson. And so we're going to use dilations on a graph in conjunction with other transformations that we've learned. So they're called similarity transformations when we do more than one. So our learning target is to find similarity transformations to map one shape to another. And in order to do that successfully, you'll need to remember how to do translations. Remember that's moving left, right, up, down. Um, reflections, which kind of reflect something over a line of reflection. So we kind of jump over a line of reflection. And rotations, which will kind of rotate around a graph. We talked about those as well. And then dilations is the new one, the one that changes size. So a couple things to remember. When we're saying congruent, that has to do with translations, reflections, rotations. Those all keep the same shape and same size. Whereas similar shapes, which we're going to be working with today, again, they have the same shape and still will have all the same angle measures, but the size will change, and in this case, the location might change as well. So some of those reminders to be successful today. If you know those things and you can perform these things, then you will be successful on a graph, or on our lesson today using graphs. So there's our problem. We want to get from shape A to shape B. But how? That is our question. So I would like you to look at it. If you would like to pause, try it. See what you could get, how you could get from the other, even visualizing it. What certain transformations would we use? Translations. Do you think we have to slide it? Would we use a reflection or reflections? Does it have to rotate at all? And since it changed size, we should know that dilations will have to happen. This one will have to happen because it changes size. So let's take a look. If I'm looking at from red to blue here, very patriotic, yes, I know. Um, I'm trying to decide if I would do a rotation or a reflection. And I'm thinking to myself, I almost think either one could work. If you did a rotation, and this would have to be 90 degrees or clockwise or 270 counterclockwise, I think I would get my P would be here, my R would be here, and that would leave my Q right here. Maybe it's up one. Actually, I think it might have been right the first time. Yeah, it was right the first time. And that would do a rotation. I think I could also make it work with a reflection over the y-axis. If this is my y-axis, the R doesn't move. The P has to go 2 on this side, and the Q has to go 1, 2, 3, 4, 5, 6, 7, 8 on this side. And it's the same shape as what would be that 90 degree rotation. So either way, if I did a, so my first one would have to be either a rotation 90 degrees clockwise, or we just showed that a reflection uh, over the y-axis would work to get to the same spot. And either way, they would end up here, here, and here. So there's my new triangle in the new spot. It should be the same shape, same size, just moved. Now, That's not exactly my new shape, though. So I have to do something different to make it larger. And that's where it gets a little tricky. How do I know exactly how much larger to make it? Do I guess twice the size? Do I do I guess at all? Well, you don't have to guess. Take a look at, let's just say we look at one set of coordinates or two sets of coordinates. Coordinates are best to look at because when we're dealing with diagonals, it's hard to tell exactly what the length of the sides are. So this is 2, 0, and I want to get to 3, 0. So no matter what I multiply by, the 0 is going to stay the same. But how do I get from 2 to 3? 2 times what equals 3? Well, if you think about when we solve the equations, you can just divide by 2, and that something will be 3 over 2, over 2, or that ends up being 1.5. So really, if you want to find the scale factor, you just kind of reverse it and divide the bigger by the smaller, or the second one by the first one. So it would be a scale factor, come on, of 1.5. And that would change all the coordinates. Okay? So let's just answer some of the questions here. I think we kind of answered already now looking at that shape. So here's an example of how you could do it. We said we could do flipped or reflected over the y-axis, and I think it does work to do it rotated as well. Um, it might switch around the variables a little bit, the points, but we'll go with it. And then dilation of 3/2, or that's the same as 1.5. So let's answer the questions about this. Number 2, what line of reflection is used to transform triangle PQR to triangle LMN? So that's assuming we're doing a reflection. So we said that's over the y-axis, because over the y-axis, that's the only way you can reflect it over to get it to mirror and kind of be in the same orientation as the blue triangle. So y-axis, and it mirrors it properly. Number 3, what scale factor and center are used to perform the reflection image? So, yeah. So, scale factor we said was 3/2 or 1.5. Scale factor we'll abbreviate as SF. Now, the one part that's a little bit different is what's the center? We're going to almost always use the center of the origin. So the center is 0, 0. Oops. 0, 0 is our center. It's almost always going to be the center of a dilation on a graph. Just assume it's going to be the center unless told otherwise. All right, number 4. Does it matter if it's first dilated and then reflected, or does it have to be first reflected then dilated? Well, we did the reflection and then dilation. Let's try it the other way around. If I were to multiply, this is -2, 0. Let's multiply by 1.5, and you can check that on your calculator. You end up getting -3, 0. And it actually will, this will multiply that there, this will get there. Actually, it'll go up higher, but we don't have the room. So it does actually work to dilate and then reflect. So either way will work. All right, number 5. Suppose triangle LMN is the original figure and PQR is the image of the sequence of transformations. What would change the description of the transformations? So now we're assuming we're going the other way. Let's just say this is our first shape, and this is our second shape. So something we talked about last time was if you go from a bigger shape to a smaller shape, the scale factor is going to be smaller than 1. So instead of doing 3 over 2, we'd have to flip it around, and the dilation scale factor would be 2 over 3. It would actually be just the reversed. Oops. It has to be reversed. Instead of 3 over 2, it would be 2 over 3. Because that's a number that's smaller than 1, so the shape will get smaller. And we'll do some more practice with that as well, exploring that. Problem 5 shows that a dilation with a scale factor between 0 and 1 shrinks the polygon. What do you think is the effect of a dilation with a scale factor of 1? So we said bigger than 1, enlarges it. Scale factor of less than 1 shrinks it. Oops. So what about if the scale factor equals 1? Well, if you multiply a coordinate by 1, what happens to it? It stays the same. So it actually does not change the size at all when you use a scale factor of 1. So I'd like you to try one problem then by yourself. This is number 7 in your notes. It says try it. It says triangle UV or shape UVWO is similar to triangle, not shape, triangle, rectangle DEFO. Describe the transformation or sequence of transformations that would take UVWO. So this is our first one to here. All right. Pause it. Try it. Sorry. Pause it. Try it. Unpause it when you're ready. All right, so real quick, I noticed right away that this thing needs to turn because the longer side is on the top here, but the longer side is on the right here. So I need to rotate it 90 degrees to the right, so that's clockwise. That's what I want to do first. When you do that, it actually lines up so it's like this, and then it goes up like this. After the rotation, it needs to shrink. How much does it need to shrink? Well, if I look at the side lengths or the coordinates, it's 1 and the whole thing is 3, or it's 2 and it's 6. So that means it's got to either be 1/3 or 3 over 1. And I'm going from bigger to smaller, so that means that my scale factor has to be smaller than 1. So that means I have to pick the 1/3 as my scale factor, because I use those side lengths of 1/3. So if I multiply all the sides by 1/3, I will get the smaller shape. So that's why the scale factor is 1/3. Now, you're going to be able to do more of this with our practice, but this is just an overview of the learning target to finding similarity transformations that map one shape to another on a graph. All right? And that's section 2020, similarity transformations. Have a good one.